We are MIT people, there's nothing we can tackle. We actually design these things. So, hello everybody, welcome to Sydney Pacific. My name is Willie, and I'm chair of the Committee of Scholar Interactions, which is also known as CoSI. And our goal is to connect people like you and people from all of the MIT community to have really nice scholar interactions, intellectual interactions with each other. And so let's get to the point. This year we have seen an unprecedented hurricane season, and we have 3 consecutive events that struck America and Caribbean islands, which is Harvey, Irma, and Maria, creating more than $100 billion of damage. I think I quoted this from Wikipedia and probably quoted from other sources. Now some of you may have may have any questions, at least I have. So what on earth is happening? Has these hurricanes have any roots with the climate change? And how can we predict future hurricane risks in the, say, if climate changes or not? And today we are pretty lucky and honored to have Professor Emanuel to answer these questions for us. Professor Kerry Emanuel is one of the most prominent meteorologists and climate scientists. He is Cecil and Ella Green Professor of Atmospheric Science at MIT Department of Earth, Atmospheric and Planetary Sciences, and is also co-founder of the MIT Lawrence Center and an elected member of National Academy of Sciences. Apart from research, he is active in propagating climate sciences to the general public. He has defined the science of climate change at a House Committee on Science and Technology hearing in 2011. And published multiple articles in prominent international media. Now, please join me in welcoming Professor Kerry Emanuel.
Well, thank you very much, Siwei. It's nice to be with you here all this evening. Do I need the microphone? If I don't use it, can you hear me all right? Would you rather I use it?
I think the mic might help.
Need the mic?
Yeah, thank you.
Okay, I'll do that. So this particular hurricane season reminds us that hurricanes are very damaging and destructive. And what my research has done in the last 30 years is try to understand how climate change, whether it's natural climate change or man-made climate change, influences hurricane activity. There's another side to this question, which I'm not going to address this evening, but which is really fascinating, which is, do hurricanes affect climate? We usually think of it in the other direction, but there's actually quite a bit of evidence that there's a strong feedback of global hurricane activity on the climate system. So what I want to do with you tonight is to sort of review where this particular scientific endeavor is at. So the program is to begin by looking at the global hurricane hazard, how damaging are the storms, and then get into scientific inferences about the relationships between hurricane and climate. We're going to begin with the empirical side. That is, let's look at historical records of hurricanes, and I'm going to show you that they're too short by and large and too poor quality to make much by way of inferences. But then I'll get on to a very new endeavor which looks for signs of past prehistoric hurricanes in the geological record. Then we're going to go to a little review of the basic physics of hurricanes, which is extremely interesting, and how can we use those physics to understand how hurricanes are related to climate. Can we also use those physics to assess in a useful way the risk from hurricanes? And I'm going to wind up the evening by focusing right on where we're all sitting, the MIT campus and its surrounds. What is the risk to this place of hurricanes? Because I'll tell you right now, it isn't zero. And it's a lot more than MIT wishes that it were. We'll get to that. So hurricanes collectively around the world, and by the way, the generic word for this phenomenon or phrase is tropical cyclone. Hurricane is a provincial word that's used for storms in the Atlantic and Eastern Pacific, but I'm going to be sloppy about that and probably just refer to them as hurricanes. About 10,000 deaths per year globally since 1971, which is pretty bad. $700 billion, 2015 dollars per year in damages on average since 1971. And the really shocking thing and the most disturbing thing is demographic, that the population, the global population exposed to tropical cyclones has tripled since 1971. And it's done that mostly because all over the world, but particularly in developed countries like the United States, people are moving from inland locations to coastal locations. And so that's part of what's driving a very large increase in damages. So I want to review for you what is it exactly about hurricanes that are risky. Well, when I say hurricane to you, probably most of you think correctly that this is primarily a windstorm, and they are phenomenally large windstorms. Winds can exceed 200 miles per hour at the surface in the most violent hurricanes. But in point of fact, the thing that kills people is usually not the wind, it's water. In the form of rain, freshwater, torrential rains and hurricanes, as we, for example, saw in Hurricane Harvey about a month ago, a little bit more than a month ago. And especially the storm surge, which is the same phenomenon physically as a tsunami. If any of you have seen the horrible videos of the tsunamis in the Indian Ocean in Japan over the last few decades, you know what I'm talking about. It's the same thing, but it's driven by wind rather than by shaking the seafloor. And I think it's so important for people to understand what this is that I've taken the risk of seeing if I can play you a movie. This is an amateur video taken in Typhoon Haiyan, which affected the Philippines in 2013. So you can watch this. The guy who filmed this is quite lucky to escape with his life. Unfortunately, the whole thing is washed out in this projector, but you can kind of see what's going on there. You do not want to be caught in a storm surge. If you're ever in a hurricane-prone area and somebody tells you to leave because there's a risk of this, you should not ask any questions. You should just get out. Okay? You can't survive that. And if we look just at the United States over the period 1970 to 1999, this is just the cause of deaths associated with hurricanes. Most of it's fresh water. It's just inland flooding from rains. The next most deadly is salt water. By the way, globally, those two are reversed. The storm surge or saltwater drownings are more important on a global scale. And wind is quite far down the list, and then there are a few other miscellaneous things. So it's really water, and yet it's arguably the least understood. And that has to do actually with a peculiar piece of economics. But around the world, and the United States is a good example, that water damages are publicly insured. For the United States, they're insured by something called the Federal Flood Insurance Program, established in 1968. And because it's the federal government, there's not a lot of effort, and certainly not much money expended in understanding this aspect of the risk. If you go down to the wind, on the other hand, that's privately insured. So if you have a homeowner's policy, usually wind damage is covered. And the insurance industry, which is a big industry, has put a great deal of effort. They hire people, like people from MIT, to try to understand the wind risk better. And they're pretty successful at that. So we know much more about the wind risk than we do about the water risk quantitatively. And yet, water risk is by far the larger risk. So we have this strange problem. Now let's get back to the science of this. So what can we learn about the relationship? Well, the first thing we want to do is look at historical records. So before about 1943, what were the records of hurricanes? Basically, they were anecdotal. Newspaper reports, eyewitness accounts, ship's logs. Very, very little quantitative measurement was going around. Now, 1943 might seem like a long time ago to you. It's not so long ago in my book. Okay, it wasn't that long ago that we weren't taking measurements at all. Historians are good at what they do. They go back through the newspapers of coastal cities affected by hurricanes. But it's a lot of hit and miss. And before, actually about the before the 70s, there were probably storms that occurred, like the proverbial tree that falls in the woods and nobody sees it. You have no idea whether it actually happened. Beginning in 1943, we started to do routine airborne reconnaissance of hurricanes in the Atlantic and typhoons in the Western Pacific. We actually flew airplanes into them. We continue to do that in the Atlantic today. I've been on quite a few of those missions. They're not as exciting as you might think they are. But in the early days, it was dangerous. They lost a fair number of airplanes. And the reason why is, if you stop and think about it, if you're in an airplane, what is this that you can measure about the storm? Think about it for a while. Of course, you can measure the temperature and the pressure where you are, but you can't actually measure the wind. Now, you know exactly how fast the airplane's going through the air, but that's not what you want to know. You want to know how fast the air is moving over the ground. So how did they do it? They flew very low in the day, and they looked at the ocean surface, and they said, boy, that looks like 100-mile-an-hour wind. That's what they did. That was in the record books. And you can imagine sort of biases that were going on in that. Who knows? I mean, they didn't have a lot of experience looking at ocean surfaces with 100-mile-an-hour winds, and they didn't have any other kind of thing. So the big advance was made right here at MIT, at Vapor Labs, with the invention of inertial navigation, which is just that. It sort of basically uses gyroscopes to measure accelerations. And integrate the acceleration over time, you get a velocity, and you integrate the velocity, you get a position. So they actually knew how fast the airplane was moving over the ground, and of course, how fast it's moving through the air, and they could deduce the wind speed at the level of the airplane. So that was a big advance, but not until 1958. By about 1970, we think we had more or less global coverage of the Earth by Earth-orbiting satellites. And satellites are great for detecting tropical cyclones, but they don't even today do a particularly good job measuring them. We can see that they're there, but actually measuring them quantitatively still requires in situ measurements. We started to measure wind speeds at the surface, but not in the hurricane core from satellites, but beaming down radiation, microwave radiation, and watching it backscatter off of capillary waves. You can infer the stress. In 1987, we lost ground on the measurement front. We quit flying airplanes. The Navy quit flying airplanes in the hurricanes or typhoons over the Pacific. So we lost that capability. And I'm going to show you briefly later in the talk a brand new technology that just came online this summer, and it's still being calibrated, a new technology from satellites for estimating surface winds. Let me show you what the historical record says, and in the process of doing that, show you the weakness of it. What I'm showing you here is strictly for the Atlantic. Now, the Atlantic is an interesting place. About 11% of the world's tropical cyclones occur in the North Atlantic. They get about 99% of the press. But most storms on the planet occur in the Indian Oceans, Pacific Oceans. Yet we have by far the best records in the Atlantic. What I'm showing you here is a time series going from 1851 to the present of just the number of major hurricanes, that is, hurricanes with wind speeds over about 120 miles per hour. And there are two different subclasses that if you add them up, you get the total. There is the blue curve you see there is hurricanes that either passed over the Lesser Antilles on the eastern side of the Caribbean Sea, which were highly populated islands through this whole period of time. Is that okay? I don't know where that came from. Anyway, so they're very likely to have been detected. And the red curve are the storms that didn't pass through the Lesser Antilles. I should say the blue curve is Lesser Antilles or U.S. mainland landfall, one or the other, or both. So the blue curve we have some confidence in the red curve we have far less. And you can see that if you look carefully at this, there's actually a statistically significant upward trend in the number of major hurricanes in both of these subsets, although it's about 3 times as much for the ocean storms, the non-Lesser Antilles or US continental storms. Why is that? Has there actually been a faster increase in ocean storms? We don't think so. It's possible. It's just that in the early part of the record, we very likely missed storms that didn't make landfall. We just didn't see them. We had no way of knowing they were there. So this is illustrating a problem with the historical records. Oh dear, this didn't come out very well at all, but you can barely see on the screen that these lines that are sloping upward at the top, downward at the bottom. What you're looking at is the latitude, a time series of the latitude at which tropical cyclones reach their peak intensity. That's something we think we can detect well from the satellite. It goes from 1980 to about the present, and the upper graph is for the northern hemisphere, and the lower graph is for the southern hemisphere. And you can see that, I think you can see barely, that the slopes of the lines are opposite. In the northern hemisphere, they're going further north, in the southern hemisphere, they're going further south. In both hemispheres, they're reaching their peak progressively over time, further and further away from the equator, further poleward. And that's something that was predicted theoretically. It's one of the few actual climate signals we think we can detect today with satellites. Now, aside from the historical records, including satellite records, we're beginning to appreciate prehistoric storms through a new endeavor called paleotempestology, the study of ancient storms. There are different techniques. Some of them rely on the very interesting fact that the chemical composition of hurricane rainfall is distinctly different from normal rainfall. If you want to know why, come and ask me at the end of the talk. It's very interesting. But there is an easier to understand mechanical thing, so I'm showing you, just focus on the top chart there, a kind of a vertical cross-section through a typical beach that you might find along the eastern seaboard or the Gulf Coast, where you have the deep ocean over on the left, something called a barrier beach, a lot of sand dunes, and behind those sand dunes, typically you find a marsh and or a lake or a lagoon. And in that marsh, in that lagoon, under normal circumstances, plants ranging from microscopic plants all the way up to macroscopic plants live and die, and their remains settle into the marsh or the lagoon, causing decay into kind of an organic mud. Pretty nice, boring process. But when a hurricane comes along, its storm surge will wash over that barrier beach and wash sand into the marsh or the lagoon. So if you fill a rubber dinghy with graduate students, which some of my colleagues do, and go out into that lagoon and drop something called a coring device that takes a core down into that lake, what you see is a lot of dark mud with sand layers interspersed, and the sand layers are interpreted to be the signatures of the hurricanes. The mud can be radiocarbon dated, so you can figure out when those sand layers were put down. Remarkably, in a few places, you can go back as far as 7,000 years. And again, I'm sorry about this. When I gave this talk before, there was no problem with the charts, but there's some mismatch between my machine and this projector. Let's just focus on the top chart. It is data from one of these cores that was taken in Vieques, which is an island just to the east of Puerto Rico. And on the left-hand side is about 7,000 years ago, going up more or less to the present. And those upward, and what you're seeing is a measure of how coarse the material is in this core. Those upward spikes correspond to very coarse material, probably sand, and they correspond to hurricanes. What's interesting is that you can see some clustering, and it's statistically significant. So there's this period here, with quite a few storms, and then this period here with almost none. So we're beginning to see, fluctuations on timescales of centuries in activity of hurricanes in Vieques. Now, one thing we know we can't do is interpret this as fluctuations over the whole North Atlantic, because when we look elsewhere, like New England, because these cores have been taken not very far away from here, we see something completely different. We may also see centennial variations, but they're not in phase with these. So we interpret these to be fluctuations in the trajectories of hurricanes rather than existence. Now the middle diagram is a different kind of proxy in a totally different part of the world, in the western part of South America, which is not a proxy for hurricanes, but a proxy for El Nino events. And those upward spikes correspond to strong El Ninos, which we know today from observations suppress Atlantic hurricanes. And what you see, if you stare at that long enough, you might be able to persuade yourself that where there are a lot of El Nino events, there aren't very many hurricanes, and vice versa. So this is one place, it's just one location. We're beginning to sort of flesh that out. Okay, let's talk a little bit about physics. Okay, I think this is the part that interests me. Some of you, well, let me just ask, could I have a show of hands of everybody who's taken a freshman or sophomore thermodynamics course here at MIT? Okay, a lot of you guys have. All right. Well, you probably remember that in the course of learning about thermodynamics, you talked a little bit about heat engines, which are just a mechanism for turning heat energy into mechanical or some other form of energy. And in the middle of the 19th century, the French physicist Sadi Carnot, who was later credited for founding the field of thermodynamics, reasoned that you can't convert more than a certain fraction of heat energy into mechanical energy. And that fraction has a maximum value for a particular thermodynamic cycle, which today bears its name as a Carnot cycle. And if you read a thermodynamics textbook, they never give you an example. They'll give you a cartoon, but not a real-world example of a Carnot cycle, because there aren't any real-world, except there is, and it's a hurricane. They haven't caught on to that fact yet. Hurricanes, remarkably, are the most efficient engine that you can imagine for converting heat energy into wind energy between two fixed temperatures. So let's see how that works. This is a cartoon. It's a vertical slice. The axis of the hurricane is at the left. We're going to idealize the hurricane as circularly symmetric. Some of them almost are. And steady in time. And again, some of them almost are. And so it's a good place to start. And so you're going out 200 kilometers, up 16 kilometers, and that white apparition on the left is supposed to be the eye wall cloud, which is where most of the wind and rain occurs. So if you do the thought experiment of attaching yourself to a sample of air at A, you would spiral around the storm, but also drift in toward the center until you're at B, and then you would go rocketing up this eye wall to 15, actually as much as 18 kilometers in reality, and out to very large distances, and over a very long period of time, 2 weeks, you would eventually come back down to where you started. Now, of course, in nature, it's an open cycle, and you never do come back down, but in models which behave more or less the same way they do. The lurid colors that you see are a measure of the entropy of a combination of dry air, water vapor, and condensed water. It's a variable that you can't change except by an external heat source. And the big ones in this case are the ocean, transfer of heat from the ocean. And the big loss is from infrared radiation to space. Now you notice that the entropy going from A to B increases a lot, and that's the firebox of this heat engine. It is transfer of enormous quantities of heat from the ocean to the atmosphere. Most of that transfer occurs when the water evaporates, just as the water evaporates from your skin when you get out of a lake, swimming in a lake or something, you feel cold. Heat of vaporization is being supplied by your body. It doesn't disappear, it gets added to the air. Well, it's the same thing. The heat source in this case is the ocean. This is made possible by the fact that the ocean is, in the tropics, is not in thermodynamic equilibrium with the atmosphere. And that's a very interesting story about why it isn't, but it's profoundly out of equilibrium. The basic reason for that is the greenhouse effect. The fact that the atmosphere traps infrared radiation. Heat can't get out of the ocean except by evaporation. This is part of the problem, because when you put more greenhouse gas in the atmosphere, you have to increase that evaporative potential. Anyway, the entropy increases from heat transfer from A to B. B to C is adiabatic. This entropy of this combination of dry air, water vapor, and condensed water doesn't change. C to D, you're losing the entropy you gain from the ocean by infrared radiation to space. And then D to A is another adiabatic leg. A to B is isothermal expansion. B to C is adiabatic expansion. C to D is isothermal compression. D to A is adiabatic compression. Voila! Carnot is vindicated there as his engine. And it's very efficient because the temperature of the surface is around 300 Kelvin, about 33 degrees or 32 degrees C. 27, sorry, about 27 degrees C. And the temperature at the top of the storm, peculiarly enough, is some of the coldest temperatures you can find anywhere on the planet, including Antarctica. It can be easily minus 80 degrees C, or around 200 Kelvin or so. So the thermodynamic efficiency is about a third. So it's a very efficient engine by natural standards. The interesting wrinkles is that to a large extent, the hurricane's actually doing no useful work on anything. It's dissipating all that wind energy in a turbulent atmospheric boundary layer. And that, oddly enough, puts heat back into the front end of the engine, which makes it run faster, but you're not violating Carnot's theorem because you're not doing any work on the environment. But knowing that, we can actually calculate what the largest, by equating the dissipation in the engine to the generation of mechanical energy, we can come up with a sort of E equals mc squared of hurricanes. And I'm not going to be showing you a lot of equations, but I have to show you this one. This is an equation for the largest theoretically possible wind speed you can have in a hurricane, and that's called VPOT for potentials. We call that potential intensity. Its square is given by three terms. The first term in box there, in the box, is the ratio of the coefficient that governs, the non-dimensional coefficient that governs how fast you can evaporate seawater. The other, the base, C sub D, is also a non-dimensional coefficient, which we call the drag coefficient. That's how much momentum goes into the water for a given wind speed. This middle term, the temperature of the ocean divided by the temperature of the top of the storm divided by the latter, is a modified thermodynamic efficiency. And then the last term, I should be going down this list here, the last term is the driver. It's essentially a bulk measure of the difference between the ocean temperature and the atmospheric temperature. And it's a term that owes its existence to the greenhouse effect, and that's the big driver. Anyway, we can calculate this potential temperature rather easily, potential intensity rather easily. And here is a map from just ordinary climatology of the annual maximum at every point on the planet. As you watch the seasons go through their cycle, you pick off the maximum value of the wind speed in meters per second. So the deep reds are around 80, about 200 miles an hour. Close to what we observe in those regions. And when you get down much below 40 meters per second, that is into the blues, it's nearly impossible to have a hurricane down there. And this actually quite nicely delineates those portions of the world that experience hurricanes. That's a long-term climatology. I'm going to show you a bunch of instantaneous maps. This is fairly recent. This is on September 5th at midnight Greenwich time. A map of potential intensity, and Irma was in progress at this time just north of the Dominican Republic, going into places where the potential intensity was getting close to 90 meters per second, which is one of the reasons we worried about it, and with some justification. And I thought I'd throw in the most recent potential intensity map I could get my hands on, which was yesterday morning, okay? And you can see how much it's diminished. This is just the ordinary seasonal cycle, all right? And if January, if I showed you January, it'd be essentially 0. All right, so does this have any bearing on real storms? So one of the exercises we've done is to go back into the historical records during the period that we think they're more or less reliable. Look at the peak wind speed in each hurricane over its lifetime, divided that by the potential intensity, where and when that hurricane occurred, and then just count it. So that red curve could be interpreted as the, let's look at this. This is the normalized wind speed. So 0.6 means the maximum winds were 60% of its potential, if you will. And this would be the number of storms that exceeded that normalized wind speed. So we call that a cumulative frequency diagram. And I've said there are two curves. Turns out because it seemed to naturally separate. These are for storms that reach nominal hurricane intensity of 33 meters per second or more. And the blue curves are storms that didn't. And one of the great mysteries is why these two curves have different slopes and what do those slopes mean. The interpretation of that is if you know nothing about the individual storm, there's an equal likelihood of it achieving any intensity up to its potential intensity and 0 likelihood that it will exceed that. So it is indeed an upper bound, but most storms don't live up to their potential. Now, when you warm the climate, this potential intensity demonstrably goes up. It should theoretically, we see it going up. So this is a trend. This is just the trend over time of potential intensity. It has nothing to do with real hurricanes. It's just the background thermodynamic potential for them. From 1980 to 2010, where you see red, it's going up as much as 3 meters per second per decade. A few places it's going down, but those places are places that don't experience hurricanes. In the hurricane belts of the Atlantic and Indian Ocean and Pacific, it's going up. If you apply this to a climate model going forward over the rest of the century, you get a similar kind of answer, that you see trends in potential intensity that are generally positive, especially outside the deep tropics. It's sort of the margins of the hurricane belts. There's a very good reason for that, which I won't go into, but that led us to predict that we should see a poleward drift in the latitude at which hurricanes reach their maximum. And as you saw before, or didn't see because of the graphic, but should have seen was that indeed satellites are detecting this poleward drift. Now, we can therefore make some very basic inferences from the theory. Potential intensity increases with global warming. And we would deduce from that, together with this constant cumulative probability, that the incidence of high-intensity hurricanes should go up over time. And as I just said, the increases should be faster in the subtropics than in the deep tropics. And another piece of physics, which is much simpler, which I haven't told you until now, is that, as you all know, warm air can hold more water vapor than cold air. It's just the Clausius-Clapeyron equation. Numerically, it's about a 7% increase in the mass concentration of water per degree centigrade increase in air temperature. It's a lot. And so we expect hurricanes to rain more going forward because the air going up into the hurricanes has a greater mass concentration of water. Models show that. The theory is very simple. Nobody really disagrees about that. On the other hand, measuring rainfall is very difficult, much more difficult than wind. So, all right, if we have some understanding of the physics, can we use the physics to quantitatively estimate the risk? And this is something we're sort of pioneering here at MIT. You might ask, well, why don't we just run a climate model, a great big global climate model, and just look at the hurricanes in that model and see what happens. So this is cutting in and out, but maybe it's where I'm standing. There is a technical problem today with doing that, and that is that the spatial resolution of today's climate models aren't anywhere near up to the task. If you look at the global models, they actually do produce things that look like hurricanes, but they're big, fat, sloppy things that don't reach very high intensity. What you see here is a histogram of the number of hurricanes whose peak lifetime intensity is what you see on the x-axis there. The black is from observations. The red is from a very good global model. And the vertical line just separates category 2 from category 3. And basically, what we know from statistics of past hurricanes is that all the damaging events, almost all of them, are to the right of that vertical line. The far more numerous weak hurricanes don't do very much damage. So what this tells us is that the global climate models can't simulate damaging hurricanes. And they probably won't be able to do that for some time. So how do we deal with that? Well, one way we do it here at MIT is we take the large-scale climate from the climate models, but we embed in that climate a very specialized hurricane model that was actually developed as a forecasting tool originally. It's coupled to the ocean. Hurricanes churn up cold water from the deep, and that limits their intensity sometimes, so we have to couple it to the ocean. It's very fast. You can run a track on this in about 5 seconds on an ordinary laptop. So you can afford to do hundreds of thousands of events this way. And what's special about this model, this is something that's very rarely done today in fluid mechanics, is that it's circularly symmetric. That's kind of standard. But the radial coordinate isn't radius. That is the independent variable in the differential equations. We've transformed the PDEs so that the space we're integrating in is not z versus r. It's z versus basically angular momentum. And the angular momentum, m, as you I'm sure know, is just the radius, the moment arm, times the circular velocity v. But we also have to add the second term, which is the projection of the Earth's rotation into the local vertical. So theta is the latitude, omega is the angular velocity of the Earth's rotation, r squared now is the radius squared. And so we recast the equations with m as the independent variable, and this enormously simplifies them, reduces their nonlinearity. This didn't come out very well, but this is just a cartoon actually taken from a model. It's not a cartoon, but it's from a model. The center of the storm, again, is at the left radius, and each one of those colored lines, which you can't quite see, is a surface of angular momentum, and they're evenly spaced in angular momentum. And what you're supposed to see, quite is that angular momentum surfaces are really packed together in the eye wall. That's where you need the resolution. And the more intense the storm, the more packed they are. This is a really beautiful computational trick, which people used to use somewhat in the 70s, 60s and 70s when computers were really slow compared to today. And the attitude now is, why bother? Well, I think there's a very good reason to bother with that. It's just a much better system to integrate. And we have been running this actually since about 2001 to forecast the intensity of real hurricanes. And what you see here is a chart showing a measure of the intensity error as a function of the forecast lead times. So 12 hours means a forecast for 12 hours from now, 24 and so forth. Of course, the further you go out, the greater your errors. And the y-axis is the root mean square difference between your forecast wind speed and what was actually observed. So the black is from the National Hurricane Center. It's a very good forecast. It's subjective, but it uses lots of guidance. The blue is from a very complicated model that you have to call the power company before you switch on. It uses a lot of juice. And the red is from a model you can run on your laptop. And there are, at 36 to 48 hours, no question the full model performs better, but not that much better. So we feel some confidence in using this toy model in a way that I'm about to describe. So how can we use that model to assess risk? So what we do is kind of interesting. We start with a large-scale or global state of the atmosphere, time evolving, varying in space, from either a climate analysis or from a climate modeling. That's our first step. We start with that. And then we initialize the specialized hurricane model completely randomly. That is, if you think of it, we take proto-hurricane vortices, seeds, if you will, and scatter them randomly in space and time into this climate state. And then we watch where they go. They simply move with the large-scale flow. That's well known from observations in theory. Tropical cyclones, just like corks in a stream, move with the flow in which they're embedded. But the critical thing is to run this intensity model along each of the tracks. And when we do that, the intensity model predicts that a very large percentage, like 98% or 99% of those seeds you put down just die because you put them in a bad environment, not conducive to their development. So we use kind of a natural selection algorithm, the survival of the fittest seeds, actually the seeds that were put in the best environments. Remarkably, it seems to work when we compare it to present day. So this small fraction of surviving events is regarded as the climatology of hurricanes. And even though it's a small fraction, we can easily generate, say, 100,000 such events. Here is a map showing the tracks and in colors the intensities of about 1,000 out of 100,000 or so storms from a current climate analysis. This is not a climate model, but just an analysis of the current climate, time varying, but not with any sort of climate drift in it. And you may have seen maps like this for real storms or may not, but we of course want to look at much more careful statistics to compare those to real storms. One of the many tests we do is to look at the histogram over a large sample of their wind speeds. So this is again an exceedance frequency, the number of times that winds larger than the value you see on the x-axis are observed. The red is from a very small sample of these MIT synthetic tracks. The blue is from history, from observed hurricanes. And we more or less capture the whole spectrum of intensities in these storms. We even get the year-to-year variability of the Atlantic storms pretty well. So this is blue is the observed number. It's not the number of storms. It's something called the power dissipation, which is an integral over the life of the storm of its peak wind speed Q, the measure of how much energy is dissipated by hurricanes. Blue is from observations. The red is from this method applied to a climate data set. So many, many different tests. Now we can take that method and run it forward by applying it to climate models. And I'm going to show you one. Oh dear. Well, okay, I'm going to show you part of one. What's missing from going from the computer to the screen is a red shading that shows you the scatter among the 8 climate models we downscaled for this. So the red curve is again this power dissipation, but it's actually power dissipation at landfall. So it's a measure of sort of the destructive potential of storms from about now until the end of the century. And it slightly more than doubles, is projected to slightly more than double at the end of the century. And the red is the mean, the standard deviation is on here, but you can't see it. It's actually pretty large. Right? There's a lot of scatter among the different climate models that we applied this method to. But most of them show some level of increase, that is, if we do nothing to curb the emission of greenhouse gases. Now, once we have these storms, we can couple them to hydrodynamic models of storm surge. And well, this doesn't come out too well, but this is a map of the Northeast. You can see New York City more or less at the center and Long Island. And those blue dots, those blue and red dots are the grid points of a very sophisticated hydrodynamic model that's used to generate storm surges. So when you let the hurricane winds interact with this model, produce surges. And we can do that for, again, thousands and thousands of storms. And this is a study This graph is from a study we did in 2010 for the city of New York, and predicting a surge at the Battery, which is the southern tip of Manhattan where there happens to be a tide gauge. And when we did that, we got this sort of projection of measure of the risk or frequency of surges. So on the y-axis is the peak surge height in meters, the Battery. And on the x-axis is a measure of frequency. It's this peculiar quantity called the return period. It is literally the inverse of the annual probability. So a return period of 500 years here corresponds to an annual probability of 1 in 500. All right. And so we predict that. That was a few years before Hurricane Sandy actually hit New York and caused a large surge. That was Sandy's surge relative to mean sea level. And if you look at that, you can see it was roughly a 500-year event. That is, we think Sandy surge in Manhattan, not anywhere on the East Coast, but just in Manhattan, was a very rare event for New York City. I won't show you this, but we will actually run projections in the future, and unfortunately it becomes increasingly less rare going forward. Let's apply this technique to Texas. So we had Hurricane Harvey, and what we did was to run 100 events, synthetic events, each year from 1980 to 2016, so that's 3,700 events, passing within 300 kilometers of Houston. We can filter the events so that they meet that requirement. And we used three climate analyses. And we also did the same thing, but for a slightly different period of time, for storms passing anywhere over the Texas coastline. This method I've been talking about produces not just wind but rain, which is very important. So we calculate the total rainfall at each point for each event, actually not for each point, but for each of 78 points in a grid covering basically southeastern Texas. And then we finally ran 100 events each year for two periods, 1981 to 2000 and 2081 to 2100, again passing within 300 kilometers of Houston from 6 different climate models run for the last century and for this century under a business as usual emissions scenario. Here is a map of accumulated rainfall for one event of these many, many thousands we produce that happens to look a little bit like Harvey. This is a storm that came in from the Gulf of Mexico. This is just a map executed. The Texas coast is here. I know you can't see it. It executed a little bit of a loop and went back out to sea. And this is the accumulated rainfall in this event. If you look at this axis, this is in millimeters. The peak rain was over 1 meter. It's well over 3 feet of rain. So that's what we're seeing even this data set is a very rare event. It produced a lot of rain because it stalled, just like Harvey did. Now, when we look at all the events that are near Houston, we get, this is a slightly different chart because the return period is now on the y-axis, but this is storm total rainfall in millimeters on the x-axis and the return period. And by that reckoning, and things are a little bit strange here, but Harvey, that line is supposed to, this is supposed to point to the 5 millimeter line, which you can't see, but it intersects this at around 2,000 years. So in the climate of 1990, for the metro Houston area, we expect a heartbeat about once every 2,000 years on average. If we look at the whole Texas, the whole southeastern Texas, 500 millimeters of rain, Harvey's rain, is something you'd expect to see about once every 100 years. Okay, so it wasn't that rare, and somewhere in Texas you would see something like that every 100 years. Now this is looking at the climate models. The blue is for the end of the 20th century, the red is for the end of the 21st century. Harvey's event goes from, again, around 2,000 years at the end of the 20th century to about 100 years at the end of this century. So that is, a large part of it is due to the fact that there's a lot more water in the air by the end of the century. Some of it due to the fact that storms are systematically moving more slowly, so they're lingering over fixed points longer and producing more rain. Same kind of analysis. This is too bad because this is such a beautiful satellite picture of Irma. Same kind of analysis for Irma, 100 events per year for these two different periods of time. But we're looking at events that pass within 300 kilometers of the island of Barbuda in the northeastern Caribbean, downscaled from 6 climate models. And now we're looking at wind. So the wind is on the x-axis. Irma's wind speed was 160 knots. And if you look at this graph, it may be something like an 800-year event in the climate of the last century, but something closer to an 80-year event in the climate at the end of this century. So a pretty big increase in probabilities of high winds because of the intensification of the storm. Hurricane Maria, same kind of analysis, different point in space. Maria's wind of 150 knots is maybe a 150-year event at the end of last century, becomes a 15 or 20-year event by the end of the century. So when most places we look, by the way, there's the scatter among, in all the graphs I just showed you, there's a scatter among the climate models, which I can see in my screen and you can't see, all right? So we're trying to quantify the uncertainty, and I'm sorry that that's not visible. All right, let me wind up with a work in progress, which is us, MIT. The Charles River is separated from Boston Harbor by a dam. It's where the Science Museum is. And at high tide, the top of that dam is about, I think it's something like 1.8 feet over high water. Not a lot. You can't build that dam higher because you'd have to also build it out, and there's no way you could do that. Water in the Charles is regulated by 6 enormous diesel pumps at that dam that continuously pump water out into the harbor. The problem that we're worried about is if you have a hurricane coming up the coast, and yes, we do have them in New England, they're not as common as in the tropics, they're typically preceded by a day or two of very heavy rain. And so you get a lot of fresh water flowing into the Charles River. But when the storm itself arrives, it could fairly easily overtop the dam. And so that fresh water has no place to go, and it builds up and it floods. And I have a colleague, very clever and nice guy here in Civil Engineering Department, Ken Struzpek, who is a different kind of hydrodynamicist. He models the flow of water around buildings, through storm sewers, around food trucks. You've the level of detail. And so we've been working on this project. So the raw storm risk, again, you can't see the scatter on this graph. This is rainfall around Boston, the probability. So storm rainfall on the x-axis, return period on that axis. The blue is from the end of the last century, the red for the end of this century. Big, big increases in probability or reductions in the return period. And then we look at surge at the Charles River Dam, and likewise we see a pretty hefty increase in the probability of surges when we go from the last century to the end of this one. And so if we build sea level rise, about a meter, we're expecting general sea level rise at the end of this century, it becomes a really big problem. That is, we're going to overflow the dam on nice sunny days at high tide. We put it all together, and we create maps like this. This is the map showing the water, or do you recognize the MIT campus? The water around the MIT campus, representing the 100-year event, that is the annual 1% probability event in the year 2070. So not even at the end of the century, and we're flooding large parts of the campus. That big white island in the Charles River is a graphical glitch. I said this is a work in progress. This is one of many, many different charts we're trying to produce. And to get MIT to plan for the risks associated with this, which include the possibility of flooding much of the nano building that's under construction, flooding the control room of our nuclear reactor, which is underground, not very far from where we're sitting tonight. There are all kinds of risks that we need to deal with here at MIT. So let me wrap it up. Observational record is too short, nasty, brutish, and short, if you will. And quantity is too low to make very good inferences about climate signals. Satellite data do show this migration of peak storm intensity toward higher latitudes. We're making good progress on paleotempestology, getting records of prehistoric storms from the geological record. There are not very few people working on this. This is a great kind of intellectual opportunity as far as I'm concerned, even though I'm not a geologist. I think it's a great thing to do. Hurricane theory, the energy theory of potential intensity, demonstrates beyond much doubt that the thermodynamic limit rises basically with temperature. It's a little bit more complicated than temperature, but that's sort of the zero order thing. And observations show that it is going up. And physics of hurricanes, we know well enough that we begin to use them and not just historical statistics to estimate risk, both in the current climate and in future climates. Rain of Harvey's magnitude was probably a 1% probability event in Texas in 1990, but should be an 18% annual probability in this century. And if you just interpolate the frequency, not the return period, to 2017, it's already gone from 1% to 6%. So was Harvey caused by climate change? Well, of course you can't. That's a badly posed question. What you can say is the probability of Harvey is going up tangibly over time. Irma's peak winds of 185 miles an hour within 300 kilometers of Barbuda are estimated to have an annual probability of just 0.13% in 1990, increasing to 1.3% in 2090. So that was a very rare event by any measure, even in a future climate. The frequency of storms and Maria's intensity may increase by approximately tenfold by the end of the century. And MIT has a not negligible flood risk today, and this looks like it's going to increase pretty fast over the century. And sorry to leave you with that gloomy thought, but you will have graduated by then.
Professor Emanuel for this such a phenomenal lecture, and we will now take questions from the audience.
Thank you. That was a very interesting lecture. I was just curious, over what interval is the storm data taken to develop those recurrence interval estimates? Because I was thinking, if you limit your the interval over which you take data to the past, like say 10 years, do you know how those numbers change? Because it always seems like the recurrence intervals underpredict frequency, right? Like I think I've heard the term like, oh my gosh, this was a 100 or a 200 or a 1,000 year storm about a couple dozen times in my lifetime, and like you'd think that you would maybe hear that once, so.
I don't think this is working. Can you hear me if I shout? So that problem you just described, the 100-year event having occurred 3 times in the last 5 years, it's in my experience, mostly a definitional problem. So let's think about this. The probability of a house in Texas being hit by a tornado in any given year is extremely small, right? The probability of a house somewhere in Texas being hit every year is essentially 100%, right? So, if 3 years in a row you've had 3 houses destroyed, journalists will say we've had 3, 10,000-year events in 3 years. You see what's going on there? Now that's an egregious example that anybody would, but they get messed up when they talk about Harveys, right? A 2,000-year event for Metro Houston, all right? Next year, we may have a flood like that somewhere else in Texas, but it's only a once-in-a-100-year event for Texas. So all these things have to do with being fussy about definitions. Yeah.
Next question.
In the outline, you mentioned some new satellite technology, some new satellite sensing
yeah.
technology.
Yes.
Could
I
you
didn't
give
show it.
You didn't show it, so could you give us a sense of just
Yeah.
a quick overview of what the latest and greatest is on that front?
I guess I moved, I was worried about running out of time and moved it, so I'll just give you a quick. This is called Cygnus, and it's ingenious. It makes use of the fact that there are GPS signals from satellites all over creation. And so what you do is you field a special fleet of lower orbiting satellites that detect GPS signals. They detect the signals directly emitted by the satellite, and they detect signals that are forward scattered from the ocean. It turns out that the fractional energy forward scattered is a function of the roughness of the surface. And the roughness of the surface is a measure of the wind speed. That's the essence of it. And the nice thing is that GPS signal length is 19 centimeters, which is not appreciably absorbed by rain. So it goes right through the rain, which is new. And so you have all these satellites. This is the, this is why I didn't show it. Beautiful on screen. This is the Gulf of Mexico and Harvey, and each of these, this is a map, and these are just swaths of the GPS signal going across the thing and being detected. And the colors show an estimate of the wind speed. But this, none of this has been calibrated yet. This is brand new. But theoretically, we should start to get really good surface winds from this instrument. Oh, I'm not the engineer, but it's limited by the number of receivers you have. But the current thing, we're going to monitor most storms, you know, every few hours. And I think in the future, much better than that.
At the beginning of the, sorry, the microphone's are weird. At the beginning of the talk, you said, or there's a slide that said like the global exposure to hurricane risk has tripled since the 1970s, but that during the same time period, the death rate has been constant at around 10,000. And I was wondering why there's a discrepancy.
Well, actually, I didn't say that. I just said there was an average of 10,000. But you are right. I mean, if you actually look at it, there's been a downward trend in deaths. And the reason for that, it's very interesting and subtle. First of all, first and foremost, we're getting much better warning. So the second thing is we're much better prepared. So let me give you a concrete example. In 1970, a tropical cyclone over the Bay of Bengal roared into what was then called East Pakistan and killed, and I'm not kidding you, 500,000 people. 500,000 people, one storm. It was horrendous. And West Pakistan, which is on the other side of India, the central government failed miserably to provide relief. And that was the instigation for East Pakistan to become Bangladesh, which it is today. Now, in the meantime, NGOs have gone in massively, mostly funded by the World Bank, I think, and built all over this low-lying river delta these, they call vertical evacuation shelters. They're just great big, cheap concrete buildings on pillars. And there's so many of them that just about everybody can walk to one in an hour. And then people don't have cars. You know. So they put out the warning, people go there, they climb up into these shelters. It's, you know, it's not comfortable, but it's okay. And they survive the storm. And so the death tolls are way, way down. In the cities, you know, it's much more, if you're in a modern city and you don't do something stupid, you'll survive the hurricanes. And that's another, there are all kinds of things going on. I know what you picked the question.
We'll take one more question. Evelyn.
I kind of feel bad.
So I kind of feel bad having this be the last question. I just wanted to know about how often they signal that there is a hurricane coming and how often they have to go up into those
The airplanes?
Yeah.
Sure. Okay, so the question is how often do we, I think my interpretation of the question is how often do we have to go up into fly up into hurricanes? Is that weird?
No.
Okay.
How often, the story you were just telling, how
Yes.
often they really receive the alert that there's a
Oh.
hurricane coming in and have to.
I see. Yes, well, in Bangladesh, fortunately, it's rare. You know, maybe once a decade, they actually have to use their shelters for that purpose. I don't know what they're used for the rest of the time. I'll leave that to your imagination.
So, thanks for as Emanuel. We have for you. Let's probably give a bit more applause for this is our second series. And so everybody that has received my email that you can attend the dinner with the name tag, please get around here and we will have Sydney guide you toward the room. Thank you.